due to it. It's a welcome session, and it will include also an honor lecture by Fausto Guzzetti from the National Council of Research, CNR, in Italy. The session will be hosted, chaired by Michele Calvello from the University of Salerno. And the program of the 24 hours will be copied into the chat for you, for those of you who haven't got it handy. I would ask you to mute your microphones during the sessions if you are not talking, and use the chat for interaction, for feedback on the presentations, and for questions. And now I would like to hand over to Michele Calvello for this first session, and I wish everybody a very interesting workshop and an interesting 24 hours. Please, Michele, the floor is yours. Thank you.
Thank you very much, Alexander, for introducing the event. I will share my screen so that supposedly you should be able now to see. Here we are. Okay, to see the initial slide. It's an honor for me to introduce the event. It's a 24-hour marathon that we decided to organize, the LandAware MayDay, around-the-clock conference that will start right away. I will not talk much in this initial welcome session because, as Alexander already said, I see Fausto is already connected with us. He is the key person of this session. He will restage for us his recent Sergei Soloveitch medal lecture that he gave at EGU in April. Before that, I will just spend a very short time, a few words about the MayDay event and also about LandAware and the photo contest. So the round-the-clock conference is going to be a full seamless day of landside early warning systems, discussions about it. No halts in the program. We will go on for 24 hours straight. Of course, not all of us will be there for the entire 24 hours. We will have panel presentations, panel discussions, Q&A, interactive sessions, many different topics. And of course, they will be all related to landside early warning systems. It's going to be mostly live, although a few times we will have some pre-recorded presentations or material for you. Every hour, at the hour, new session, so easy to remember. If you need to take a break, you know when to take it, and you can come back at any given hour for the beginning of a new session. That's why we will be on time, because all the different sessions are independently organized. So choose what you want to follow, simply connect when you can. Don't stress if your time zone doesn't allow you to attend the session that you wanted to attend, because as you read, we are trying to register these, and hopefully it will work. We cannot promise the result, but we will try to register the sessions so later you can watch them on demand. But that is not a promise, again. Check the program whenever you want to see what's coming next. The web page is there for you to check what's coming in the next 24 hours, really. So with that, I want to say, 24 hours ago, we checked, Manfred did this for us, and we had 220 participants from 43 countries. Indeed, by now, we are more than that, at least in terms of registered participants, 279 from 49 countries. I'm pretty sure that the count will go up slightly, or maybe not slightly. Anyway, at the end of the day, I will tell you what are the final figures about this. Very few words about the network, because you can read. Maybe most of you know it, some of you don't. It's a network of individuals, not a network of institutions. And the idea is to share. It's to have a venue for sharing experiences, needs, and innovations among both experts, researchers, in order to develop and promote best practices indeed. So we are it's a new network. We were born just last year. I can say that we set up a network with a bottom-up structure. So we are thinking that really the engines of this network will be the working groups. So different working groups doing, dealing with different topics, issues, engaging in different activities, at the end coming together in this network. But indeed, the working groups are the places where things will happen, hopefully will happen. And then we'll have also gatherings like this one, when hopefully we can all come together and share these experiences. There is an executive committee. Indeed, the executive committee, it is the founding members of this network. Last year, after a long genesis, also coming from previous meetings, physical meetings, when we could meet in person, good old times. And hopefully they will come back soon. Anyway, it's 9 of us from all over. You can see many Europeans. You can see Dalia Kishban from NASA and Hiro from Japan, as well as Joanne, Katie, Graziella from Northern Europe. Manfred, the real host of this meeting, he was the guy doing the job for this meeting. And then from Italy, me, Stefano Galliano, and Fausto Guzzetti, a founding member of the network that will talk right away. Just give me a couple of minutes. The working groups, as I said, they are the main operational units of LandAware, and they're formed to address specific topics, and they're set up with a clear mandate. They operate continuously over a fixed period of time, depending on what they do. There is always 1 or 2 coordinators, and then people joining the working groups, either as associates or as observers. At the moment, we have 7. We set up those 7 at the beginning, last year when we created the network, but we really think that, in the future, we will have more and more people will get involved. So without further ado, I move on. And okay, there is one final thing before moving on to Fausto. You may know that we also set up a photo contest. If you don't, or if you didn't, I'm telling you now. You can go to the web page where all the pictures that came before yesterday, up to yesterday, 15 photos are there for you. Of course, here you can see them. They are very small, but there you can click and check them full size. And then we ask you during this day to vote for your favorite photo, to vote only once, of course. But it's 15 pictures. You can choose what you like the most. There is a clear link to an easy Google form where you can choose your favorite photo. So this is about it, because I want to leave most of the time of this session to Fausto Guzzetti. It is a pleasure for me to introduce him. And also it is a pleasure for me to say that, he accepted to restage for us what his lecture that he gave at EGU this year. EGU was also an online gathering this year, as that's what's happening in these pandemic times. He will talk about considerations on the prediction of hazards, mainly landslides. That's the title, as he put it, and their consequences. And I thank Fausto a lot. He took also a picture where others were thanking him as well when they were doing their laudation for his lecture. And I asked him to come show the camera and also the screen, because I can indeed stop sharing my screen and leave the floor to him. Thank you, Fausto. The floor is yours.
Okay, thank you. I presume you can see the screen now. Right?
We can, yes.
You should be able to see the screen. Sorry, I'm going to slide number 1 for some reason. So thank you, Michele, and thank you for the opportunity and bless the privilege of giving an honorary lecture at the opening of this LandAware MayDay 2021 round-the-clock conference, a peculiar setting. To be honest, and to reiterate was what Michele has said, that this is the same talk I gave almost exactly a month ago on 22nd April at the EGU 2021 General Assembly. So if you were at that presentation, do not expect anything different. Actually, you can sleep for about half an hour, take a nap and come back to be part of the discussion. In the talk, I give what is my view, and I should say my personal view, on the prediction of natural hazards and their consequences using landslides or taking landslides as a prototype. But I think the ideas are somewhat general and apply to other hazards too. And I concentrate on population of landslide, that is, predicting the occurrence of many landslides that sculpt, literally, as you can see in the images, landscapes, posing a threat to people, properties, and the environment. But what do I want to predict exactly? Well, if I say tomorrow there will be a landslide, I am sure to be right, 100%. I did not say where, and every day there are landslides somewhere. Even if I say tomorrow there will be a landslide in Italy, knowing, for example, that it will rain, I have good chances of being right. Every year there are literally thousands of rainfall-induced landslides in Italy. So these predictions are technically correct, but not useful, really. If instead I say, due to the expected rainfall in the next 12 hours, there will be 50 landslides with a volume, say, larger than 100,000 cubic meter each in a given area, I would anticipate where, when, how many, and how large we should expect the landslides. This will be a useful prediction, which we struggle to do today, unfortunately. Knowing what we want to predict, I have then organized the talk in 5 parts. The first 3 on where, when, and how many landslides we should expect. The 4th on the consequences of landslide. The last for some remarks. So let's start with where landslides are or we can expect them. Sorry, something went wrong. Here we go. This should now work. In Italy, over 600,000 landslides were mapped. This is an average of 3 landslides per square kilometers. But not everywhere we have such detailed information. In 2012, we estimated that less than 1% of the land masses was covered by landslide maps. The situation, I don't think, has changed much in these decades. And then there are the seas and the oceans that for landslides are almost completely unexplored. What is important here is that lack of accurate landslide information limits our ability to model hazards, to evaluate risk, to assess the performance of our prediction models, and to design proper mitigation strategies. For years, I should say for decades, landslides were mapped through the visual interpretation of aerial photographs. Today, satellite images are replacing the aerial photographs, and the digital stereoscopes are replacing the analog ones. With these tools, Mauro Cardinali and his colleagues at CNR in Perugia have mapped 125,000 landslides in about 11% of the hills and mountains which are subject to slope failures in Italy. And this is really a lot. It's a very large number of landslide maps, but it is a very slow process. This is why there is interest in semi-automatic or automatic methods for detecting and mapping landslides using remote sensing data. And here I show 2 examples. On the left, a geomorphological map prepared using LiDAR data in Belgium, in a forested area of Belgium. And on the right, an event inventory in Taiwan prepared from optical multispectral satellite images. But the semi-automatic and automatic methods tend to map too many landslides. To address this problem, an inventory obtained from the optical images can be weighted with some sort of susceptibility information to obtain a more accurate and probabilistic inventory map. But the optical sensor do not see below the clouds, which can persist for long periods in some areas. And this is indeed a problem. This is why people experiment with radar sensors that penetrate the clouds. And here I show the ratio of amplitude measurements of two SAR images taken before and after a landslide in Chile on 16 December 2017. The colored area is the landslide that was captured by optical imagery only weeks later in January 2018. Recently, Alessandro Montini published a review of studies that use SAR imagery for landslide detection and mapping. They are in many, really, 147 cases in 32 nations, mostly in Asia and particularly Japan. Authors have used the amplitude or phase of X, C, or L-band images taken mostly by satellites. The review showed that SAR images can be used to detect landslides that have left some kind of discernible signs in different morphologic, geologic, and climatic environments. And this is really good news. But we are far from having operational systems that can systematically detect and map event landslides. We are also interested in knowing where landslide can occur in the future. For this, we evaluate what we call susceptibility, the time invariant probability of landslide occurring in an area depending on the local settings, on the local conditions. And Paula Reichenbach led a review of more than 500 articles from 1983 to 2016 and found that more than 600 areas around the world studied in 63 different nations, but also found that most of the world, as you can see, is not covered by susceptibility maps. The review found 163 different model types, which to me are simply far too many, with the classic methods, those in red or in the chart, becoming progressively less popular in favor of more, let's say, more modern machine learning techniques. The review also found that the use of thematic variables has also changed over time, with an increasing preference for morphologic variables. This, interestingly, is not really for scientific reasons. Instead, simply because digital terrain models are easier to obtain and process. The quality of the susceptibility of models is, of course, crucial. And years ago, we proposed an index to measure this quality. However, the review showed that high quality models, these are in red, in the red colors, orange and red and dark red at the very bottom of the chart, are really rare even in the recent years. And this is a serious problem. I said before that we assume susceptibility to be time invariant. However, by studying a multi-temporal inventory, we saw in an area in central Italy, we saw a temporal dependence of new landslides on the older ones. In this study area, and particularly when a landslide happens, it sort of becomes an attractor for future landslides for the next about 10 to 15 years. And this violates the assumption that susceptibility is time invariant. To address this issue, we tested a Bayesian in the same area. We tested a Bayesian framework with a Poisson part to model the expected number of landslides in each slope and a Gaussian part to account for the spatial distribution of the terrain settings that control failure occurrence in that area. We built 5 models. We tested their intensity and susceptibility performances, and we prepared even combined intensity susceptibility zonings for various time periods. This is probably the most advanced prediction model I've worked on and the closest to a complete landslide hazard model. But space-time modeling requires multi-temporal landslide information that is difficult and therefore expensive to obtain. And this is a problem. We now move to the temporal prediction, which can be for short or for long periods. For short-term forecast, we use rainfall thresholds, and on the left, you can see the famous Kane 1980 global thresholds for debris flows. Or you can use physically based models, and on the right, I show an early model by Montgomery and Dietrich in 1994. And I now concentrate on rainfall thresholds, which are a very popular theme in the literature with several, let's say, issues. For example, for intensity duration thresholds, intensity depends on duration, and this is a problem by itself. The data to define the thresholds are often limited and of dubious quality. The method used to select rainfall events are often unclear, and many thresholds are difficult to reproduce, and also uncertainty is hardly ever given. In synthesis, my take here is that I see a lack of rigor, of scientific rigor in the definition and use of rainfall thresholds for landslide forecasting. And with my colleagues at CNR, we have done work to address these problems over the year. First, we devised criteria and algorithms, which we coded into open source software for the objective definition of rainfall events, of the rainfall condition that can result in landslides from those events, and of rainfall thresholds. I think that availability of open algorithms and software is instrumental, I should say is crucial to obtain reliable and comparable thresholds. Next, we collected a large number of high quality data following a somewhat rigorous protocol. This graph here shows more than 2,300 rainfall events with landslides in Italy from 1996 to 2014. And using our algorithm and software, we defined the thresholds for different non-exceedance probability. Here I show 4 of them for 5, 20, 35, and 50% exceedance probabilities. To investigate whether the thresholds depended on the local conditions, something that many reviewers of our paper have suggested, we segmented the catalog and obtained thresholds for different conditions. As you can see, the thresholds are indeed different. The analysis also revealed something interesting. Thresholds for different mean annual precipitation domains, in Italy at least, but also in other areas, become higher as the mean annual precipitation increases, which in other words means that more rain is needed in raining areas to trigger landslide than in less raining areas. Like any other empirical models, the thresholds are affected by a level of uncertainty, shown in the plot here by the colored areas, and as you can see, it's not small. In practice, it is difficult to separate uncertainty from variability, and this complicates matters, particularly if the thresholds are used in early warning systems. And indeed, the idea of a geographical early warning system is a landslide early warning system is not new. Is not recent. In 1975, Russ Campbell of the USGS proposed that a warning system could be made with 3 main elements: a system of rain gauges to record the rainfall on an hourly basis, that's what he postulated at the time, a weather mapping system capable of recognizing centers of high intensity rain, and a system to manage the data and inform residents. And he concluded that, and I quote, "Such a system is probably within the capability of existing technology." That was 46 years ago. Recently, we examined 26 geographical landslide warning systems, including 19 regional, 6 national, and 1 nearly global system, Dalia's one, considering design, experimental, operation, and even dismissed closed systems. We found that the system operates in all climates, with the majority in temperate regions, 61% of them, in all geological domain virtually, and in all seismicity zones. And this is really good news because landslide warning system can work anywhere without climatic, geologic, seismic, or tectonic constraints. But are the existing systems in the right places? Well, the distribution of recent, being 2004 to 2017, non-earthquake induced fatal landslides, these are the green dots in this map from a work by Frood and Patley in 2018, shows that many areas where fatal landslides are numerous and the risk to the population is therefore high, are not covered by early warning system. And this is a problem. We also found a lack of standards for the design, implementation, management, and validation of the systems, and for the way in which landslide forecasts are provided to various audiences, including authorities and the general public. The graph here is a bit complicated, but in summary, it shows that virtually everywhere system uses its own approach. I think these are serious problems that can limit the credibility and in the end, the usefulness of landslide early warning systems. Here I show two operational forecasts. On the left, one for Italy in September and October 2015 for a period of 5 weeks. And on the right, for an area in southern Italy, the Gargano promontory, for a period of just 5 days. And in this last plot on the right, the gray dots are the landslide that have occurred. And you may wonder how good these forecasts were. It is actually hard to say because we often don't have the data to verify the forecasts. The lack of automatic landslide detection and mapping system limits our ability to verify forecasts. And this is a serious problem. Coming to the long-term projections, I must say that we are less good with our projection, and I think for 3 main reasons. First, we lack reliable time series. The one I show is one for an area in northern Italy. The series are typically sparse, with a few days with landslides and many, probably too many, without landslides. And also the series are clearly non-stationary. And this complicates the analysis and the interpretation. A cause of non-stationarity in the system is climate change. And Stefano Gariano prepared this map that shows where 139 landslide climate studies have been done from 1983 to 2018. They aren't many, really, and with a biased distribution that you can see clearly on the map, with many studies in Italy, France, and the UK, and almost none in Africa and also in Oceania. Indeed, the problem is very complex. It depends on meteorologic, climatic, and environmental variables. Different landslide types respond differently to changes in climate, and the scale, the physical scale of climate and landslide are, of course, very different. And here I show the expected changes in the abundance or activity of 4 landslide types. These are rockfalls, debris flows, shallow and deep-seated landslides due to the predicted climate changes. Most of the arrows, as you can see, point up, indicating a projected increase in the abundance or activity of the landslides, but there are arrows pointing down and are also conflicting projection locally. We need more studies, in my opinion, in more areas to better understand the long-term impact of climate on landslides and to make projections that are really useful and to predict the response of landscapes dominated by mass wasting processes. And Massimiliano Albioli used rainfall measurements and synthetic rainfall projections in central Italy to force a spatially distributed, physically based slope stability model and obtain 2 what I consider relevant results. First, the distribution of the size, in this case, the area of the projected landslide, will not change in this particular study area, which is important for hazard modeling and risk assessment. Second, the rainfall condition that can cause the landslides in the area expressed by rainfall thresholds are instead expected to change from about 2030 onward in this study area. And that is relevant for landslide early warning based on rainfall thresholds. We now move on to the prediction of how many landslides may occur, which means predicting their size. If you look closely at a landslide map, you can see that there are few large, many medium, and very, very many small landslides. And only recently, fairly recently, we have discovered that this distribution are not at all random as they may appear, and that the size of the landslide follows empirical laws, as do, for example, earthquake or aftershocks. We found the scaling law for landslide areas and volumes, which I show here, and also for the area to volume and the length to width ratios. These scaling relationships are very important for hazard assessment and to design proper landslide impact scenarios. But unfortunately, we do not know what exactly control the statistics of the size and the number of landslides, although we have ideas, but this limits our ability to use these statistics. We come to the consequences, which means anticipating vulnerability and risk. Vulnerability to me is easy. We know almost nothing, or well, at least I know almost nothing. Here I show an attempt to link the size of landslides of the slide type to the proportion and type of damages to building and roads of two different types in central Italy. And as you can see, the spread in the data is really very large. And since we do not have enough information, we often take vulnerability at its maximum value, corresponding to complete the destruction, but this overestimates risk, and it's a serious problem. In Italy, we are better at predicting risk to the population, thanks to a catalog of landslides with direct human consequence that was compiled by Paola Salvati and their colleagues over many years. And here I show the geographical and temporal distribution of more than 1,000 fatal landslides from 1861 to 2015 in Italy. And with this information, what is landslide risk to the population of Italy? Well, it really depends on what you consider. If we consider the maximum number of fatalities caused by a landslide, we see this. If we consider the number of landslides with fatalities, regardless of the number of the fatalities, we see this. If we consider the proportion of landslides with few, many, and very many fatalities in an area, we see the blue map. Three different maps. And how do we use them? Well, Mauro Rossi overlapped the maps and obtained a distribution of societal landslide risk in Italy. There is a wealth of information in the map that we must learn to use in order to give appropriate messages to the population and the authorities, knowing that landslides are not gender neutral, at least not in Italy. In Italy, landslides have killed more males than females. Age also counts. The maximum number of deaths is between 30 and 39 years old for males and between 60 and 69 for females. Now to my final remarks. The gray area in this space-time plot is the domain of hazard and risk assessment I've presented, and the colored rectangles are the example I have shown. An additional domain is the stability of single slopes, which I have not really discussed. This is a complex world that I have explored only partially, with relationship between landslides, landscape that host them, and the hazard and risk they pose. Landslides respond to energy input, being it precipitation, earthquake, or even just topography. They do it in a non-stationary context at multiple spatial and temporal scales, adapting to meteorologic, climatic, and geomorphologic changes. And they self-organize to go from stability to instability conditions. For better hazard and risk assessment, in my opinion, we should combine regional and local models with new models capable of operating at different scales, a bit like meteorological models do. Monitoring is also essential, of course, but we need to know what to measure and why, and how to manage the data properly. We need standards for data, maps, models, and their validation, which we lack currently. And we need to work on communications. Now, allow me some final philosophical remarks on prediction. The use of science in general to anticipate the future, which means making prediction, in modern terms date back to the 19th century. At the time, the physicist Heinrich Hertz wrote, and I quote, "The most direct problem which our conscious knowledge of nature should enable us to solve is the anticipation of future events." And he went on writing, and again I quote, "For the solution of this problem, we always make use of our knowledge of events which have already occurred, obtained by chance observation or by pre-arranged experiment." This positivistic perspective is counterbalanced by theoretical and practical limitation. Here I will mention just one. David Wolpert has shown that there cannot be a computer that can process information faster than the universe does. In other words, our models cannot have the same details and resolution as reality, and we have to live with that. Predicting hazard, in my opinion, is a difficult, complex, and uncertain endeavor of scientific interest and societal relevance. And to those of you bold enough to accept this challenge, I say that there are two groups of people who make prediction. These are fortune tellers and scientists. The difference is that scientists can explain in clear, unambiguous, and transparent language how they make a prediction. It is vital that we all act as scientists and not as fortune tellers. A final remark. In a recent book, Nassim Taleb, the author of The Black Swan and other books, in this book, he suggests to avoid taking advice from someone who gives advice for a living unless there is a penalty for their advice. As hazard and risk predictors, we give advice for a living, and we should be ethically involved in what we do. Well, think about this the next time you give or ask for advice on natural hazards. That was all. Thank you. Thank you for listening.
Thank you. Thank you very much, Fausto, for this very interesting presentation. Sorry. And so now we have time because we planned these in advance to be, for me to be quick in the introduction and for Fausto to keep in these 25 minutes. That was the length that he had for his talk. Okay, we have time for questions. And as I said, you can raise your hand. You can even unmute your phone, your microphone and talk because it's not very many of us. I think it's going to work. Or you can use the chat. I can see there is something on the chat already. So Fausto, I can read it for everybody, but you can read it yourself as well. Editian says, on a regional scale, when dealing with landslide early warning, we can't still pinpoint the exact slope that can slip. Is there a model that you can point towards that can tend towards this?
Well, landslides are very erratic phenomena. The uncertainty that are associated with our models are very, very large, unfortunately, as I have seen. At the regional scale, the models that are used now are based on threshold models or similar statistical models. So linking the outcome of that models to any specific slope or portion of a slope remains a challenge, and I will not do it at this time. It's a challenge of when I said that I look forward to people that merge empirical, statistically based and physically based model working at different scales. That's exactly what I was referring to. So this is actually ground for new research.
Thank you for that. And I see, okay, even the person who asked the question is thanking you. And I don't see anything on the chat as a question. I see, congratulations from many people. As I said, you can even, unmute your mic and we can talk. In the meantime, maybe I will ask something to Fausto, because you ended up by saying that somebody said that you should be aware of people giving advice for a living, and indeed most of us are doing that in our daily life. What is your experience now that you moved from an institution that was the institution of a very important institution in research, and you were heading a very large group of people? I know you've been doing a lot of experience there, CNR, and being the head of that research center. Now that you moved to the civil protection, and then I think it's almost 1 year or even more than 1 year that you're there. What's the situation? What changed? You're doing a different job, on a daily job. What can you tell us about it?
It's actually a very different perspective, a very different point of view. Sitting here, one realizes that it's very different. It's a very different perspective from science, and it's not only for landslides or hydrological processes. These days we have problems, for example, with active volcanoes, for which we have prototype early warning systems that are run, for example, by universities, but it's very difficult to have the sound and robustness that a system needs in order to operate it for civil protection purposes from a university. There is also an issue of responsibility when you are in a research center or a university center. Everything is experimental, everything is a prototype, and so that everything is on quote easy from that point of view. When you apply it on an official level, you take responsibility levels that in Italy are very high. So from country to country, because it depends on the local legislation on this. But regardless, the perspective is very different. And to one extent, I see it's more difficult. It's a more difficult perspective. Maybe we don't even, the amount of information that is already available from scientific community is probably enough, and we are not using everything that we know already. So from my point of view, maybe we don't have to advance the science too much. We have to spend more time in applying the science we already have. And communication in particular, I stressed this point in the talk in a couple of places. Communication is really crucial from a number of point of view.
Thank you very much. I see that there are 2 questions in the chat, but before there was a hand raised by Nejan. You can talk.
Hi, thanks Fausto for a very nice lecture. My question is about the low quality susceptibility maps you mentioned. Have you seen cases where they are dangerous? Should they be discouraged, or they are still at least useful from nothing at all? What do you think about that? And second part, with all these uncertainties and like impossibilities, how do you keep your motivation to solve this challenging question every day? Thank you.
Well, I address the second first. I mean, that's challenges for the next generation of landslide scientists. I mean, it's good to know that you have a lot of problems to solve. Coming to the first one, I think it boils down to this. People, the world, I think, again, is divided between people that thinks that some information is better than nothing. Okay, having a susceptibility map is better than not having a susceptibility map. Well, I'm not sure. At this point in my career, or from the place I sit, I think that having wrong information is much worse than not having information. And when a susceptibility map is not built following strict scientific rules, for example, is not properly validated, who knows that if that map is good or bad? You have to trust the person who did it, which in places can be acceptable, but in many other places it's not. So I changed through my career opinion, and now I'm arguing that information has to be good information, particularly for decision maker to be used. And poor information or bad information is actually much worse than not having information.
Thank you very much.
Oh, you're welcome.
We have two questions in the chat. The first one by Mirjana Budimir says, you mentioned there was a gendered and age dimension to landslide deaths in Italy. More men than women, most men 30-39, most women 60-69. Do you have any information on why that pattern is happening?
Yes, I think we have a clue. First, it's not only in Italy. We were not the first to find out. I think there was another paper in Switzerland dealing, I presume, mostly with floods, but that obtained a very similar result, which is different from other studies I've found in other countries, particularly not developing countries. They are quite old studies as far as I know. And the bottom line is that for both landslide and floods in Italy, but in other cultures, women are much less risk takers than men. We don't have a single case in the record where we had a man forging a river, for example, at ice stage, or when there was it was raining or there was a debris flow. So whereas we have several men that did that, and of course a number of them were killed. So that's one, I think, the most important reason. At one point, we thought it was due to the jobs that people were doing for a number of years in the armed forces, in the defense, but also in the police and the forest fighters. They were only men, at least in Italy. But now in the latest, say, 2 decades, that's not the case anymore. We see that bias cannot explain. So the real reason is that is the different behaviors of let's say Italian men and Italian females, with the Italian females being much less risk takers than the Italian males.
And then we have another question by Jonathan Ramos. Great presentation. Thanks for sharing your knowledge. I would like to make a question regarding the use of metrics, ROC, AUC, and others to assess the reliability of the landslide prediction on ore mapping results.
Yeah, there are plenty. I mean, if you look in the literature, and not only the literature on landslide, every time you have models and you want to check them against the other models or against ground data, you can pick up literally tens of indices or metrics. My point is that the landslide community should agree on a minimum set of metrics that are meaningful, that are really meaningful for what we do, and provide that minimum set for all the models we prepare. Then people can experiment, can play, and can publish many other indices, but those should be a basic. Let me take the opportunity to make a comment on rock, the receiving operating curve and the area under the rock and so on, which is often, to me, all too often taken as the measure to evaluate the quality of a model. We should keep in mind that susceptibility models have a spatial component to it, and which is not captured really by the rock. The rock is a lumped measurement of the performance of the entire model. But you may be interested, you may care less of errors in certain areas than in other areas. So the rock by itself can actually take the model that performs better from a statistical point of view, but which makes less sense from an operational, practical, geomorphological point of view. And this is true for most of the metrics. Metrics are very good. They tell you something. If the metrics are poor, you have a problem. But even if the metrics are good, it doesn't mean that your model is really applicable and it makes sense, unfortunately.
Thank you. We're approaching the end of the session because, as we said, we have to be strict with our organization. But we have a final question by Adityan. It's a second by Adityan, but doesn't matter. He says, you had mentioned the factor safety model in your presentation. Could you explain how efficient these factor safety models are and how statistical models have replaced these conventional models? Are statistical ones or the physical ones more efficient?
Well, it really depends on what you call but for efficient. The model I discussed is actually not ours. It's the USGS TRIGS model. It's one of the few very efficient models that incorporate physically based slope stability model. They export that on a geographical based. The problem with those models is the availability of information. I mean, you need to know hydraulic conductivity at depth. And who knows the conductivity at over 1,000 square kilometers in spatial and temporal variability. Those models, I once counted them, and I think they need 12 or so variables, of which only slope, only terrain slope or terrain morphometry is the one that you can measure accurately. The others, you sort of guess them, or you know them only at specific point. But regardless, I think that using these models in with a stochastic approach, a bit like people do in meteorology, when you run several models perturbating the boundary conditions, or adding distribution to these models for the different variables, can give you an idea. And I think the future is probably a combination of, say, statistical and physically based models. Originally, physically based models were limited to areas of very limited extent because of the data they require, the amount of data they require, but also because of the computer processing effort. They needed a lot of computer effort. Now, computers can be very fast. There, a problem is that the codes on which we use to run these models are not parallel in nature. As a matter of fact, the experiment, the results of the experiment I saw with the results of our colleague in Perugia were done using a parallel version of TRIGS. Exactly because we wanted to be able to run literally thousands of models like they do for climate projection, exactly with the same philosophy. So I don't think there is one model that in principle is more effective or efficient than another. It depends on the data you have and on what you want to get out of the model, really.
All right, thank you very much. And then Joanne, very last question, if it's Joanne, just because she came at my question is, in your experience, how many systems are making use of probabilistic forecasting approaches and capturing dynamic uncertainty?
If you refer to landslide forecasting system, very few. Very few. And this is for many reasons, including the fact that it's very difficult to handle uncertainty in the results. We have this problem in other hazards here at the civil protection. How do you cope with that? But even restraining the response, the answer to the model itself, I know of very, very little models that actually use the uncertainty that is built in the model. We did something like that for spatially distributed rockfall modeling. And we did something like this for using TRIGS in a probabilistic fashion, sort of simulating or assuming the level of uncertainty associated to each variable or to the main variables in the models. and results are interesting. It's something that can be done, but there are not very many experiences. Also because, I mean, it's a lot of number crunching you have to do.
Thank you for this. Also, the fact that you said, you know, dealing with uncertainty in the results, it's it's a good point to consider. Besides, you know, as scientists dealing with uncertainty in the model. Thank you very much for this. Thank you very much for everything, for being with, for having jump started this conference with this excellent presentation, and it was a very lively Q&A. Also, I thank you all the participants for that. I just want to share my screen one last time because I want to tell you that, you know, new sessions are coming in just a few minutes. We'll have next one with contribution from ICL president, interviews to labs experts by, you know, chaired by Stefano, Luigi Gariano, and others. So please stay with us. And now, you know, we can take a very short break, and at 3 at the hour we will start. Thank you.